is absolutely, your lit review. Now, this is when it gets complex with structured equation modeling. Let's say you have something like this. I'll just keep it a nice simple model for now. Let's have this be job satisfaction, organization commitment, professional commitment, and job performance. Which actually would not be, that'd actually be a pretty interesting model to see if commitment and professional commitment are more exogenous or endogenous. That'd be an interesting model, actually. I wonder if anyone has done SEM with both organization and professional commitment simultaneously in the model. Does anyone know if they have done any SEMs with both of those? So that being said, I want you to do a lit review. That to some degree gets at your model. And you're going to hypothesize two models. Now, what happens if you go through the literature and you do not find any articles that exactly correspond to your model? And that is going to happen. Unless you're replicating someone's findings. What if you're interested in this model and no one has ever done organization professional commitment? What would you do to justify your model? Let's say you really want to test this. You think this is very interesting. You think job satisfaction and organization commitment will be the exogenous variables. This will be playing somewhat of a role of a mediator. And then job performance. What if you found no model has simultaneously incorporated organization professional commitment? How would you justify it?
Can you find something that was as close to that as...
Maybe something that was similar. I had to do that for my dissertation 6,000 years ago on workload and stress, performance, social support. I found little pieces. Like I'd find a workload performance relationship. I'd find this relationship. So even my lit review kind of was sequestered by the bivariate relationships. And that's why I might find a path model. So you'll do the best job possible and find things as close as possible to justify it. And then part of it may be exploratory. Let's say Zach decides, I'm really interested in organization commitment, professional commitment, there's nothing out there. You may end up saying, I've done the lit review, there's a couple articles that are close to this, and this is an exploratory model. So sometimes you'll be on the vanguard. That being said, so that's the lit review. The lit review should give me a good lit review, you guys, is not just a sheer repetitive chronological cataloging of all the studies. Smith and Smith, 1902. Smith and Wesson, 1903. Smith and Wesson, 1905. A good lit review not only gives me, obviously, the seminal literature in the area that leads to the development of your theoretical model, but it tells me a story. It tells me what led to this. So by the time I'm done with your lit review, I can see exactly why Zach came to this model. I go, okay, I see the underlying logic, how Zach approached this. So to me, that's a good lit review. That's a good lit review. And they're not easy to write. It's really easy to catalog articles. Most people just look at the abstract and they lift a couple sentences, put in a couple of their own words, and pretend it's their own. Because it's hard to write it. But a good lit review logically tells me how Zach came to that model. So a good lit review. And then, of course, you're going to have your hypothesized model. And you're going to have two models. Remember, you only have to do a CFA for one of them. You only have to do a CFA for one of them. Because there's a slight chance your second model may involve a different construct. Remember, I make that clear in the assignment. And I'll leave that up to you. So your hypothesized model, please have a figure. Please have a figure. Because you should have, figure one, your first hypothesized model. In fact, there's a chance you could have up to 3 figures. Figure 1 would be your measurement model, right, the CFA. Figure 2 would be your first hypothesized structural model. And the figure 3 would be your hypothesized, your second model. So you might have up to 3 figures. Then, just discuss a little bit about your proposed analysis. In other words, you're going to do a CFA and then a full-blown SEM. Even though if you read my article in 2000 with Les Hayduck in the special issue on SEM, we said you should all do it in one step, but people still tend to do measurement model than structural. So that being said, discuss briefly the proposed analysis, the software, Amos. I want you to write it like it's a journal article. I really want you to write it as if you're submitting this as a journal article. And then the various fit indices we discussed last week. Remember, what were the main fit indices we discussed last week? Even though there's about 30 of them that Amos spits out, what did we discuss last week that I want you to report minimally? Do you recall? Among all the statistics.
Chi-squared?
Yeah, that's usually one of the first ones. And does chi-square tend to be significant? Almost always. Almost. And in your book, there's, I don't know, if, hopefully you've read the chapter on SEM in Stevens. It's a great chapter. And it's almost always significant, usually blamed by sample size, but not always. It still shows me this is an exact fit statistic. What was the next one I want you to report minimally?
Root mean square.
The root mean square error approximation, which is what they call an absolute fit index, sometimes called a badness of fit. And again, you guys, some people say 0.08 or less would be indication of problematic fit. I mean, it's good fit. Some would say 0.05. So you use your judgment. What's the other one I want you to report, as we went over last week?
The PCFI or
The CFI.
CFI?
The comparative fit index, and the NNFI, and there's a chance in Amos, it's called the TLI, the Tucker-Lewis index. So minimally, you're going to report these and the SRMR. Remember I showed you how to do that last week using the plugins option? Remember I showed you how to do that, and I'll show you again. So, yes?
Are you expecting something more complicated than this path model that one variable, another variable, or do you want something more like that where you have two of the variables covariating and then predicting something else?
Say that one more.
Do you just want like a path model, like if you took out like organizational commitment?
Oh, and then
it was just
yeah, because I'm restricting. I said you only have to use 3 variables, right?
Would it make sense to have something like job set and organizational commitment just predicting job performance, or is that not?
Well, then that's just total regression.
Okay.
Well, I mean, yeah, that's okay. Yeah, you know what? But it's a latent variable. You could have that if you didn't want to do a mediator, and I think I'd be okay with that if you can justify it.
Because you said use 3 variables, so
use 3 constructs.
That would include 4, right?
Yeah, I mean, you could do that if you wanted to just do that with no mediator.
But yeah, that wouldn't be SEM then, right? That'd be.
Yeah, it'd still be SEM because it's a latent variable. You have multiple indicants per construct.
Oh, okay.
So it still is SEM, just there's no mediators. Here you're just saying that there's no path between those. You're just saying that they covariant.
Okay.
So that would be, I'd be okay with that. I mean, it's a little less interesting than when you start thinking about mediation. And that's the beauty of this, right? You know, even though you can do a lot of this in SPSS with latent variables using mediation. But absolutely. Now remember, everybody, as we went over last week, your CFA, you might use 3 of these for hypothesized model 1, and you may decide to add another one for your second model. But you only have to do the CFA with one of those. If you think you're going to use 4 different ones, you could do the CFA for all 4 constructs. I'm fine with that. I'm absolutely fine with that. So again, in your report next week, lit review, hypothesized model, the proposed analysis, the indices you will be using that we just discussed minimally, and then obviously your what? What would come after that, everybody?
Interpretation.
Results. Results. I want you to look at other journal articles and see how they've reported it. Okay, there's tons of it. You can go to any journal of psychological assessment and there'll be 3 to 6 articles on CFA and or SEM. But let me go ahead and show you, just give you a little idea. Let me see something that I've done recently for a client. I've co-authored a few of these. There's one especially long one. Let me see how I did this. Let me see how I did this for a client. Give it a sec. Okay, here we go. Let me see if this is on the web.
Do you maintain your own website, or do you have someone do it for you?
I have someone do it for me. They don't have to do much work nowadays. They
Just keep up on articles.
Yeah. I give them the articles and all that. Here we go. This is what I did with the RAND Institute. 7 mark a few years ago. And we did end up publishing it, but this is the really long report from UCLA. So, yeah, this how, in fact, I went into more detail in this technical report than I did the journal article. But basically here you see I have a 3 and 4 factor model was tested via confirmatory factor analysis. Data was screened in SPSS using pre-list and Lizroll, which is a different software that I use. I talk about the multiple methods of analysis were employed to examine. I talk about the different types of estimators I use. This gets a little more technical than you'll have to worry about. So I do get some of the technicalities if multivariate normality is not tenable, which I can discuss today. Look at this. This is the whole thing I just went over with you. This is the whole section on the type of indices I'll use. I talk about the chi-square, non-normal fit index, SRMR, CFI, some of the research on it. So this is exactly what you'll be doing, everybody.
Can we report it like that, report what we're going to report? And
a little bit,
actually
yeah.
report it.
And I always do, and this is what I get from Lizroll, and this is the actual fit model, but I want you to remember, I want you to do the hypothesized one as we discussed. And then discuss the results in the body. And what I usually do, let me see if I have, yeah, okay, this is kind of a table that might help you out a little. You might want to have a little table that has, you know, your CFA, model number 2, hypothesized model number 2, hypothesized number 3, and then have the chi-square, RMSEA, almost exactly like this. I don't report GFI anymore. As we know, there's enough research that shows that GFI has a lot of flaws. So you may want to do a table like that. That comes pretty darn close to APA requirements for this. And I still want you to discuss the stats in the narrative, but you can also report this. And it'd be nice, especially to compare your hypothesized models. Like here's your CFA and your hypothesized models. And, okay, then I didn't anything. I don't think there's anything else here. This was it. Yeah, and that's on the web, and you can check it out if you like. So that being said, everybody, then you will discuss the interpretation. You said interpretation, so that's like your discussion section. So the results and interpretation, and how did we do? How did we do, everybody? Is the fit pretty good? If it isn't, why? What can you start attributing to if your model exhibits ill fit? What might be some things you could think about that possibly contribute to that? What might contribute to the lack of fit?
You're proposing the relationship may not be moving in that direction.
Maybe the wrong direction, absolutely. Wrong direction. What else? And you can think as simply as regression analysis. That might help you get an idea. Yeah, so maybe performance should have been impacting professional commitment. What else is a big problem in regression models?
Covariance.
What do you mean by
covariance?
covariance?
That they're interrelated.
Okay, maybe you've left out certain covariates. Now, are you talking about exogenous covariates, such as? What are you talking about then? Okay, you can have exogenous covariates.
Okay.
What if you wanted a control for age, sex, and number of years they've been on the job? You can actually have individual variables. If that's X1, X2, X3, and you can actually have covariates in the model. Gotta be a little careful about it, but you can have covariates in the model. And technically they should probably also have a path to the DV. That's the reason why you have covariates, because they're related. Also, omission of relevant variables. What did we call that? What type of error is that called? Omission of relevant variables or inclusion of irrelevant. What type of error is that called? You should remember from 6022. Specification error. And that's a big problem in SCM. Specification error is, Zach alluded to it by having the wrong path, omitting relevant variables, because the omitting relevant variables gets wrapped up in the disturbance terms, right? There's errors with the individual variables, and there's errors in the equation, right? In terms of the relationship of the latent constructs. And if you've left out important stuff, if you really should have had job engagement in there, and A, you did not measure it, or you did not include it, that does create problems for the model. So those are all things that, and we discussed some of that last week, but those are all things to keep in mind why sometimes your model doesn't fit. And I'm going to discuss a few more things to troubleshoot. So in your interpretation, after the results, then you'll discuss the interpretation, as you may want to start speculating, because I'm kind of constraining the samples, the database, right? I've limited it. You didn't get to measure your own variables. So here you may want to start thinking about other variables you've left out, alternative models, ways that could have made it a little bit better. So everybody, that's your paper that is due next week, and we will start class at 9, and we will have approximately 15 to 20 minute presentations. I want the PowerPoints pretty professional. I want them as if you're presenting them at APA. As if you're presenting. I'm not going to be a hardcore stickler in APA, the APA style, but I do want it pretty much the APA, and I want a professional PowerPoint presentation. As if this is something that you'd be reporting at the American Psychological Association or any other convention. So any questions then about next week's presentation? And the paper is due.
Can you show us in AMS how to look at some of the other stuff outside the fantasies? Like you said,
Absolutely.
look at
In fact, I'll do that.
residuals.
Absolutely. I'll do that right now as we move to the second part. So now, everybody, any questions on the paper or presentation, which will start at 9 o'clock next week? Any questions?
How many pages is too many?
How many pages is too many?
Uh-huh.
God, I never can answer that correctly. I don't know how to answer that.
Sometimes I hand you a stack of papers.
Well, I mean, I don't need every output known to the universe, but it's hard. That's always hard for me to say. Should it be a 20-page paper? If it's 15 and perfect, and 20 and just you've just vomited everything into the paper, then I'm not going to be as happy with that. So I've seen some short papers that I don't want to. It shouldn't. If it's 5 pages, you haven't done your job. I can tell you that. If it's much less.
No, I'm not going to.
If it's much less than 10, once you take into graphics and tables, there's not a lot going into it because there's some complexities. So I see it. God, I always have such a hard time answering that. I see it from 12 to 25. It's something like that.
That's good.
You know, so around a range like that. Okay, now we've discussed the CFA. Now you're going to find there's not much new that we're going to add today on instruction equation modeling. There's not going to be that much new with the CFA, right? Let's say we had 3 indicators per construct. 3 indicators per construct. As you recall, and the book gets into this too, if we use literal notation, this would be the what? This is, when it's just a CFA, there's no real, I mean, there are exogenous and endogenous, but we're not predicting anything per se. So here you would have let's pretend it's an all X model. Sometimes they can be all Y's, but here you have zeta 1, zeta 2, zeta 3. And maybe that's organization commitment, professional commitment, job satisfaction. Each one has 3 indicants. So again, what's the main difference we discussed last week that differentiates an EFA from CFA?
Theory.
Yes. And what else? Mathematically, what's different, Chad? You're absolutely right. Theory is dictating the relationship of the individual measures and the construct. But what else is different in terms of the estimation of the model that we discussed last week? What else is different? We did discuss this in detail last week. Anyone remember? What does this mean, everybody? What's that?
Identity matrix.
I know. What did we say last week? What does that mean in terms of the design matrix? What does that mean in that how it's different from an EFA? We discussed this approximately 168 hours ago. These 3 items are being estimated for organization commitment, but not for the other 2 constructs.
Right.
These 3 items are being freely estimated for professional commitment, but not these 2 and these 3, right?
That's So you don't have anything going on in the other one?
Correct.
Like you do in EFA?
Yes, EFA is called the unrestricted model. Bless you.
Because there's usually numbers for all of them.
For all of them. Now, they may be really, really low,
Right.
but when you get an EFA, do you still get non-zero loadings for all the other constructs and items
Yes.
relationship? But here, you are constraining. You're constraining these three items to be 0 on OC, right? I'm constraining these three items to be 0 on these two. Which means, as Chad said, what's dictating this? You or the black box? You are.
You.
Exactly. Whereas EFA, it's going to give you, right, non-zero loadings. So it's a much stronger model to support your measurement, right? Your measurement. So here, everybody, we've got your generic 3 construct, 3 indicants per construct. So let me go over a couple of issues. And I'm going to start bringing these in. Some are in the book, some are just the years and years and years I've been doing this stuff. So you will read, you got to have 3 or 4 measures per construct. You will read that a lot. That was written a lot, and there's an element of truth to it. Because one part is identifying the model properly. Model identification can get very complex. But as we discussed last week, model identification is, there's kind of 3 elements of model identification. Just identified, over-identified, and under-identified, as we discussed last week. If we have 3 items, or 3 elements, 0.3, 0.2, 0.1, 0.6, 0.5, 0.4. Let's just say we have 3 items. What's on the diagonal? Remind me what's on the diagonal? What's the unit of analysis for CFA and SEM? What type of matrix?
Covariance.
Variance covariance. So what's on the diagonal, you guys?
Variance.
And the covariance and the off
And the
diagonal?
covariance is
Okay.
off diagonal.
Right. So do you see there's P times P plus 1 divided by 2 elements in any variance covariance matrix. Right? So 3 times 4 is 12. 12 divided by 2 is 6. So you got 6 bits of information in this. 6 bits. Everyone clear on this? So what if I have this, everybody? You will be able to identify that model, right? We have this path here. We'll call this B21. We'll call this B32. So I'm going to estimate these 2 elements. And then you're going to have an error there, an error there. So you got 5 elements. Excuse me, 4. Do you see we have 6 minus 4? So we have 2 degrees of freedom. However, Zach also wants to do this. And G, Zach wants to do that. How many elements now? 6 elements and 6, which means you have 0 degrees of freedom. So do you see a degree of freedom, everybody? A degree of freedom, and the actual definition of degrees of freedom, as we discussed, means how much is known versus unknown. In structure equation modeling, degrees of freedom means the more degrees of freedom, the more you have the ability to test your model, because you're constraining some elements to be 0. So here, everybody, part of identification is if I have 6 paths, 6 parameters to be estimated, and 6 degrees of freedom, what am I left with? Goose egg. Which means that's called a saturated model. That's called a saturated model or just identified. Under-identified. Now, Chad wants to also add this. Guess what? 7 paths, 6 elements, minus 1 degree of freedom. Can't get a minus 1.
Yeah.
You can't get a minus 1, which means you're going to get really screwy results, parameter estimates that don't make sense, possibly negative R-squares. Because it means there's not a unique solution. The way to think about a unique solution, 6 plus x equals 10. X has to equal excellent. Well done.
Why aren't there questions like that? I totally passed 2nd grade. This class was true about.
Okay.
stopped myself for a second. I was like,
What's the answer? Lot of solutions, right? Is there a unique solution for that?
No.
No. That's the screwy type of stuff you get for under-identified models. No, there's no unique solution. So what we like is to have over-identified models, which means Zach has the foresight to say, you know what, there's all these paths. And you guys, sometimes, I don't see this much now, but I have seen some SEM models where people are kind of new to it, and they're doing paths all over the place, every combination, and they haven't thought about it. You're going to suck up so many degrees of freedom. It's not theoretically elegant, and you ain't going to be able to identify it. So Zach just decides on this one, where he has room to move. He has degrees of freedom, which means it's over-identified, which means you can get a unique solution. So you got to be thinking about identification of models. And that's sometimes when models screw up. That being said, that's why the old rule of 3 to 4 items per construct was it identifies the model. It does a good job of identifying the model. Because you have more elements in the variance-covariance matrix than the number of paths you need to estimate. Does everybody understand what I'm saying? You have more elements in the variance-covariance matrix than the number of paths. So that being said, everybody, can you do this? And there's a couple paragraphs in the book in SEM. What if you only have one item? Overall, I'm satisfied with my job. What if you're going to stick to that, everybody? You have basically a one-item indicator, which really is just like the manifest indicator. You can actually do that in SEM. You still have to set, as you know, as we discussed last week, you have to set one item per construct to 1.0 because it sets the scale. When you set it, it's like setting the variance to 1.0, which is a type of z-score. And what the book makes clear, when I set something, let's say it's a 1 to 7 point item, when I set this to 1.0, it's kind of like all the items are scaled to 1 to 7. That being said, everybody, I guarantee you, you will not be able to identify your model if you just do this. If you have if this is job stress, and you have one item. Overall, I feel stress on the job. You're going to have a problem there. Which means I showed you a little formula last week. And you would have had this in your psychometric class when you learned about standard error measurement. I'm assuming you learned about standard error measurement in psychometrics. The standard error measurement is a function of a variance of an item times 1 minus the reliability. Because reliability is already a squared score. So this actually, you have to set the error variance when you have a single item indicator. So when people say you have to have 3 or 4 items, if you have one great item, you can actually do latent variable analysis with a single item construct. And but you do have to fix the error variance. You have to fix it. So you have to know the variance of your variable, which you probably have from your data set, and you have to have an idea of the reliability. You have to have an idea of your reliability. So that's, again, you can have single item measures. And I do once, I just finished a project. It was actually through a marketing firm in Atlanta, but it was the American Cancer Society. And they had quite a few single item constructs. And they had no idea what to do. And I said, that's no problem. I go, what I need from you, though, is the idea of the reliability. You have any information on reliability? If the client has no idea about RxX, sometimes I'll play around with values from like 0.7 to 0.9 and see if it radically changes the model. It probably won't. So here, everybody, that being said, now we've talked about CFA. The big difference here, everybody, is this. That's how we're changing it. We're going to now add what's called a structural path. So do you see CFA was kind of like what type of rotation, everybody? Oblique or orthogonal? It's analogous to what type of rotation did we say last week? Oblique or orthogonal? Oblique, because all the constructs are what? Correlated or uncorrelated? Yes. And that's the default of all these SEM softwares. Or it should be. That's a problem, everybody. Every software has a little slightly different default. M+, Literal, EQS, Amos, all of them will have their own little defaults. You have to kind of understand their idiosyncrasies. But here, Chad is going to say, I think organization commitment predicts professional commitment, which predicts job set. And he may or may not decide to also have a path there. So here we have the same constructs, same items, which you'll do for your take home next week, but now you're adding a structural path, which is that's the regression part. That's why, literal, in the old days we were taught SEM is a smorgasbord of exploratory factor analysis and regression, right? So the EFA part we've already gone over, and this kind of reminds me of which part? The regression part, because we're predicting.
For a model like that, would you be saying that professional commitment is a mediator?
Yeah, in this path.
But so if
you know what,
if you didn't have that path from organizational commitment to job set, would you say that professional commitment only mediates a relationship and there's no direct relationship between?
If I had this, you mean?
Yeah, without that line, without that line between organizational commitment and job set? What is the difference between that?
The problem is, if I didn't have this, then technically you may not, because mediator, you kind of have to have this path to control for the other variable to calculate the indirect effects.
Okay.
Right? Because remember, the indirect effects are a function of A times B, which you'll get, or C minus C prime. Right? From the direct model, from OC to job set, and these are equivalent. So you could get by, but they usually recommend you should have a path also from OC to job set. But if you find theoretically it doesn't make sense, then you've just got maybe this type of model that's not testing full mediation. So here you have this model with 3 indicators per construct. I guarantee you have plenty of degrees of freedom. I can guarantee you. Because how many observed indicators do we have? How many observed indicators? Tell me if you need multiple choice.
Dracula.
9 or Dracula? 9, right? 3, 6, 9. So the degrees of freedom are 9 times 9 plus 1 divided by 2. So there's 45 elements in the variance covariance matrix. And I guarantee you there ain't 45 paths being estimated there. Right? Not even close. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 disturbance terms. You got plenty of room to move. Plenty of room. So you guys, once you start having these latent variable models with multiple indicants, usually you're going to have plenty of degrees of freedom. Plenty of degrees of freedom. So now everybody, you know I'm graphically challenged. It's just not my thing. Even when I did Amos years ago, I actually prefer to use the syntax. I'm just more of a syntax guy, but let's say for now, let's take this really ugly model. Again, you guys are going to get really good at the graphics. I know when I see it next week. But that being said, let's say I have interpersonal impact relationship. We see here the direct path there. And we have social support here, and we have relationship. Right, so we see here relationship impacting social support. So it's basically the relationship of interpersonal and social support is mediated by relationships. So here's the model. Here's the model. We have 3 items per construct. What does E1 through E9 mean? Error, and that's measurement error, right? That explained variance from the indicator and the latent construct. And now you have these path coefficients. You have these path coefficients. And what does res1 and res2 mean? Error in the equation, right? Or sometimes what's called disturbance terms. And you set one indicator per construct to 1.0. So not much changes. Once you go from your CFA to SEM, everybody, the main thing you're going to add is a path. The main thing you're adding is going to be a path.
Dr. Glaser, so when you press that up arrow on that top of the page, and it gives you those values for the other paths. What do those values mean? How do you interpret those?
What values? What's that?
Like if the top of the screen, like when you press that up arrow.
Right.
No, keep going. Right. That.
Oh, this.
Yeah, right there.
View the output path diagram.
Yeah. You press that, and it gives you all the what do all those values mean?
I'm going to show you in a minute.
Okay.
I'm going to show you that in a minute. This is your hypothesized model. Okay, this is your hypothesis. Now, when you do analyze everybody, I want you to go into analysis properties. So let's talk. Let's do a brief technical discussion, because I said today I'm going to add some special topics. The default that all of you will use is called maximum likelihood. That's the default estimator. We've already discussed maximum likelihood in the context of logistic regression, where you're finding parameter estimates that maximize the likelihood of the observed data. So essentially what I showed you last week, what maximum likelihood kind of does is let's say the mean of height was 60 inches in the population. Let's say the average person's 5 feet tall. How is 48 inches doing as an estimate? How's 75 inches doing? How's 62 doing? So we're getting a little bit closer, right? As we use certain estimates to approximate this. And you can calculate a probability for each of these. So here you see why you want computers. Remember I talked about IRT last week? IRT uses maximum likelihood. So it basically integrates. Right? Thinking of integration from calculus. It integrates all of these, multiplies them, and tries to find values that maximize the likelihood of the observed data. So in calculus, you have sometimes what's called local maxima and global maxima, as well as minimum, right? So sometimes it gets caught in those values. And that's why you see weird error messages from Literal. You see weird, like global minimal descent. You'll see weird error messages that I had no idea what they meant back then. And it means it's stuck there. It's not able to get a full solution. Because similar to logistic regression, similar to EFA, it uses what's called iterations. It uses iterations. It's not a closed model. So it means it puts in the initial based on the variance covariance. Then it updates the estimates as the model's improving, the fit. Sometimes it gets stuck. And it's really hard to figure out why it gets stuck. Sometimes it's what's called starting values. Maybe if you know information, if you know the correlation of job sat and organization commitment is 0.4, maybe you can go ahead and put a 0.4 in the model and see if it'll go ahead and get what's called convergence. Remember from your homework in EFA, you had problems with convergence? And I said, just increase the number of iterations. You can do that in SEM. You can increase the iterations to, you can do it to 100. See what the heck happens. If you start doing this and the model's saying converging, then you've just got a flawed model. Something is screwing. So maximum likelihood is the default and requires multivariate normality, one of the first assumptions you learned early in this class. However, I guarantee you for your take-home, you don't have multivariate normality. You know why I know that? Because you're using individual Likert items. There's no way individual items are multivariate normality. Once in a great while, but often not. But you guys will not have to worry about it.
What do you mean we don't have to worry?
You do not have to try to figure out, use the bootstrap option.
Okay.
But you could try the bootstrap, and I'll talk about that. Amos is pretty restrictive when it comes to some of these options. M+ is cutting edge. One option is generalized least squares. This also requires multivariate normality, and it basically weights the residuals. The predicted score, or basically the residuals, as you recall, are based on the actual variance covariance matrix and the reproduced one, just like EFA, and it weights it by the variance covariance matrix. The one thing that in Amos you can use, if you think you have multivariate non-normality, is this asymptotically distribution-free. Asymptotic means large sample size. This one doesn't really assume normality, but in the research has shown very clearly you need large sample sizes. It's really screwy with small. In the old days we used to use this, and now we don't anymore because it needs well over 1,000. Well over 1,000. So that being said, what do you do if you're using Amos? You got maximum likelihood, you know you don't have you know you have non-normality. Then Amos does offer this thing called the bootstrap. Amos does offer this thing called the bootstrap. When you perform bootstrap, maybe percentile confidence intervals, maybe use 200 samples, and maybe bootstrap maximum likelihood, etc. And that is, do you remember what bootstrapping is, everybody? You take many samples from a set data. So if my data is a 1, 2, 3, and if I take 200 samples, I could do 1, 1, 1, 2, 1, 1, 3, 2, 1, 3, 3, 3, with replacement. That's bootstrapping, which is actually, I'm not saying it's a panacea for non-normality, but that's what within Amos, the Amos interface, you can use in the event of non-normality. However, other software I use uses what's called the Satora-Bentler scaled chi-square. Satora-Bentler scales it by the fourth moment. Do you remember what the fourth moment in stats is? The first is the mean, the second is the variance, the third is skew, and what's the fourth? Kurtosis. It scales it by kurtosis. And it has a scaling constant, so it reproduces proper standard errors. And in M+, I use this estimator often called MLR. R means robust to non-normality. So why I love M+, why I feel it's the cutting edge software, is it's got all these estimators that can accommodate these unconventional models. But that being said, the one option that you do have is what's called these bootstrap options for non-normality. So that being said, those are, the models can tend to be sensitive to non-normal distributions. Obviously, you can try transformations, see if that helps, but I guarantee you, if you have Likert items, 1 to 5 point items, which a lot of people in psychology do, you're not going to have normality. So that's a little thing about estimation, everybody, about the different type of estimators. And so we got estimation. As you know, you're going to sometimes have missing data. It's going to happen. Amos was one of the early softwares that accommodated it. If you hit this option called estimate means and intercepts, that'll accommodate missing data. That will accommodate. See, a lot of times the means may or may not be actually tested in your model, the intercepts. So that, you'll hit that if you have missing data. And then for the output, if you have a mediator, indirect, direct, and total effects, it's a good idea to get correlations of estimates. You do get a test for normality, standardized estimates. You get standardized estimates right there, and squared multiple correlations. And then I would also get the residual moments and modification indices. So there's quite a bit you can get there in Amos. And we're going to talk about modification indices soon. And that'll be good enough, everybody. And if you want to, you can get the sampled moments. So then you go ahead and you save this. It's an AMW file, as we discussed last week. Calculate estimates. It's looking good. You can tell that around. No errors. So view, text output. Here you can see degrees of freedom, number of distinct sample moments, 54. Number of distinct parameters to be estimated, 25. So we have 25 degrees of freedom. Now, this may be confusing. I just told you there were 45 elements. Why are there 54? I just told you, right? 9. Remember I told you this, everybody? For the CFA with 9 items, 9 plus 1 divided by 2 is 45. Would anyone like to guess possibly why it's 54?
Are you including there?
The means for each item. 45 plus 9 is 54. It's including the intercepts. So here the chi-square is 95.87. Degrees of freedom is 25. You can report it as you would in any journal article, everybody. Right? As in any journal article, you would have something like the chi-square with 25 degrees of freedom equals 95.87. Reject or fail to reject the model fit. Given the probability level, given the P. Reject or fail to reject.
Reject.
Reject. Happy or sad when the chi-square results in a reject and null decision.
Sad.
Yeah, and guess what? It's going to happen. I rarely get fail to reject decisions. But here, so this is the exact fit index. So far, not looking so good, but not surprising. Here's all your estimates, everybody. There's your unstandardized estimates, and here's the standardized estimates. Remember, be careful about comparing standardized estimates, because if there's linearity, there's going to be some problems. But you can look at the standardized. Here's the unstandardized. You see those are fit 1.0. You have one per indicator. And almost invariably, the item relationships to indicate the constructs are usually significant. These are basically type of Z or T tests, asymptotic Z. And usually they're significant. Usually they're significant, and they all are. They all are, everybody. And here you see are the path coefficients. Interpersonal to relationship, 0.27. Relationship to social support, 0.611. So there's the two paths, and they're both significant. Which means so far, the individual coefficients are looking pretty good. Again, how to interpret it? As my construct goes from 1 to 2, 2 to 3, depending how you scale it, relationship goes up by 0.27. And there's the standardized regression coefficients. If some of these are really, really low, that might be an indicator of something going on. Like I see social support to its first indicator as a 0.326. I see a 0.328 of relationship in its first one. Maybe there's some problems with those. Here's the intercepts, which are the means of the items. This is just the means of the items. That's all. And then you have the variances. See, you have error variance for each of these. These are variances. These are not standardized. These are error variances. And you have the disturbance terms for interpersonal. And research 1 and research 2. Interpersonal is an exogenous construct. Exo means outside system. So that's just the variance of the exogenous variable. These are the disturbance terms. The errors in the equation. Res 1 and res 2. And you can look at the squared multiple correlations. I'm seeing some are a little bit on the low side, you guys. I'm seeing 16% is accounted for the latent construct relation, which is a little low. 18% for the third item of social support. Wow, look at that, 10% for the first construct and relationship, 10% for the first item in social support. So I'm seeing already some indications that not all is going well for this model. And you asked me earlier, Zach, where can I start looking at local fit? I can look at those multiple correlations sometimes and start seeing where some things are going screwy. If you have non-significant paths, non-significant indicators. And what's really helpful, everybody, is to look at the standardized residuals. The standardized residuals, because we used to say in the old days, if anything's bigger than 2.0, it's a problem. You don't have to stick to that, but similar to regression. If anything's over, say, 3.0 or 2.5, there might be something in the model. So for instance, look at the largest one here, everybody. I see a 3.07, a 3.88 for interpersonal 2 and social support 3. Interpersonal 2 and social support 3. Interpersonal 2 and social support 3. I put effort into building my friendships. I achieve my goals more easily with support of friends and family. Do those seem similar in your opinion or not? Maybe, so maybe you might say, hey, those are two separate constructs. They're loaded on two separate, but they sure seem different. You don't have to make any model modification, everybody, to your model. You just test your postulate and you can stop there. But usually what I would do then in my own work is I'd look at the residuals and maybe see what's going on with those items. Zach, you brought up a couple of weeks ago about letting errors correlate, because sometimes the model may say, let errors correlate. But if you're letting errors correlate, everybody, what that means is if I have E4 here and E7 here and I'm letting them correlate, you better have more than just a mathematical reason for doing so. Right? Maybe it's because these things are measuring similar constructs where something's been omitted. something's been omitted. Or maybe the word, they're responding to the method, what's called method bias. So that could be insight into what's going on. You do get direct effects, standardized direct effects, indirect effects. If you have a mediator, you do get the path coefficients. Again, there is a way of finding p-values. In AMIS, you have to go on the net, and I think it does say exactly how you get p-values. So here, everybody, this will give you an idea of how your model is doing. You may want to create a separate table and put the parameter estimates in, just like a regression model. Just like a regression model, which is what I do for my clients. And you could probably just cut and paste that into Excel. You could probably, I bet you could do, I'm sure you can do, just go down and cut and paste. So that being said, everybody, there's your estimates. There's your estimates. Modification indices. The one difference of doing SEM compared to all other statistical models is it gives you these things that say, you know what, if you delete or omit or change this path, your model will improve by so much. So modification indices, if I look at the largest one, I see an 18.8. It says, if I let the error of the 7th item, for some reason, correlate with the interpersonal construct, the modification index indicates that we'll get a parameter change of 0.203. It means my parameter will change, will go up by 0.20. But you better have justification for that. You better have justification if you ever use modification indices. In other words, if I decide that the first item of social support will now load on interpersonal, because boy, look, my parameter is going to change by 0.567, you better be able to justify it. So sometimes, everybody, you will get statistical output that will show, you know what? If I have organization commitment, also load here, which is called a cross-loading, right? What if I would have this item load on 2 constructs? Or if I have the errors correlate? Or, oops, maybe I should have had job sat to organization commitment. Again, those are all data-driven changes to the model. And as long as you're honest and clear about it, I don't have a huge problem with you having fun with modification indices. But then I always tell my client, when we do this, now the true litmus test is to test our new modified model on a different sample. Not on the same sample, because of course it's going to fit better. It's the same sample. It's a sample by which these modification indices cropped up from in the first place.
How do you explain cross-loading it? Just the item loads onto two
Constructs, yes.
constructs. And I mean,
I think it's kind of easy sometimes in psychology because things, organization commitment and job involvement, there's probably so much overlap that sometimes an item does share variance from both constructs. And sometimes it could be the wording. The intention of the item maybe is to be separate, but maybe the wording. I really enjoy, I'm very involved in my job on a daily basis. I'm very satisfied with my job on a daily basis. Maybe they're responding more to the daily basis than they are the actual construct. So sometimes it can be the wording, Zach, that will impact that type of result. It's not easy. Has anyone ever created a survey? Have you guys ever created a survey yet? Have you written one from scratch? It ain't easy, is it? If you think you got 4 constructs, 3 items, have fun trying to make them completely orthogonal from each other. It's easy to get into.
we did do one for psychometrics, and I had a couple items that cross-loaded onto the constructs we had.
Absolutely. So that's the basic for looking at the parameter estimates. And here, we already went over this in detail last week, so I'm not going to spend much time. But here we can get an idea of the overall model now. Chi-square is significant. We already went over. Remember, we discussed the default saturated model and the independence. What did we say last week the independence model was? When everything correlated what? What did we say? It's got 11 more degrees of freedom. That means everything is what? If you've gained more degrees of freedom, are you estimating more parameters or estimating less parameters? You're estimating less, which means you're setting a lot of those to 0, right? The independence means they're all 0, which is sometimes called the null model. Sometimes it's called the baseline model, depending on the software. So here, everybody, Amos spits out lots of fit indices. The norm fit index, the relative fit index, the incremental fit, which Lizerl does too. But we will focus on the TLI. It's got some of the, just statistically, it's got better properties. TLI of 0.711, thumbs up or thumbs down? What did we say generally we want?
0.9.
0.9, even though Bentler says 0.95. Yeah, guys, if you get 0.9-ish, I'm not going to come off like an editor, a reviewer, and say, well, recent research indicates 0.95. If you say 0.9 is okay, I'll be fine with that. If you say 0.711 is okay, you're way off the mark. 0.8 of CFI, again, not good. As we went over the math for both of these. They're functions of chi-squared degrees of freedom, so I'm not going to go over that again. But so far, it ain't looking so hot, is it? And right now, I've got multiple lines of evidence why the model's not fitting. The chi-square is significant. These incremental fit indices, which compare the default model with the independence model, are low. We had some really low R-squares, right? We had some pretty low R-squares, to be honest. And let's also look at the root mean square error approximation. The root mean square error approximation, everybody, which is kind of a badness of fit or absolute fit index, which is a function of a discrepancy function over degrees of freedom square root is 0.119. You'll see some research in your book says it should be at least 0.08 or less. Some say 0.05. We'll play it a little loosey-goosey in this class, and 0.08 or less will be fine. 0.119 isn't even close. And look at the confidence interval, everybody. 0.095 to 0.145. It doesn't even include the lower bound of 0.08. At least if the lower bound included 0.06, I might not be so negative about it. So everybody, that's everything except one. That's all except one. And to get the SRMR, you need to hit on standardized root mean residual, keep that box open, and it'll spit it out for you. 0.1068. 0.107. Again, some say 0.08 or less. I tend to be a little more rigorous on this because this is the standardized residuals. The standardized residuals, and I like them to be at least less than 0.05. I'm okay with your paper, 0.08. But I really do look at those very closely, and there's the standardized. So right now, everybody, when all is said and done, have we furnished evidence for acceptable model fit? In your opinion, given all the lines of evidence that we've just gone through, have we presented evidence, or it ain't looking so hot? It's not looking so hot. It really is, unfortunately. So what do you do if the model ain't looking so hot? Well, you can start playing around with modification indices, letting errors correlate, changing some paths, adding some paths. But then it all becomes theory-driven, unless you've had alternative competing models. And that's what most people usually have, everybody. Usually they don't have just one model. A lot of times they may be interested in alternative models, which is actually a very good idea to have. Now you asked me earlier, here what you get, Zach, are the parameter estimates. So you see there's the 1.33, which was the coefficient there. So these are the unstandardized estimates. And this is what you'll have in journal articles. You usually have a diagram with these. These are the error variances. And the RES2, this is the errors in the model, in the equation. So it's basically just all the parameter estimates from the actual unstandardized. Now, I'm sure there's a way to get standardized here. I'm sure you could probably play around this. I know I could do this in all my other softwares. Diagram. Let's see if I'm sure there's a way to be able to do this. You just might have to play around with it. If you want to get the standardized estimates, I know there's a way you can probably do it. View the output diagram, view the input. So there's the input, there's the output. And there's probably somewhere here you can get the standardized estimates. You'll have to play around with that. So the default is the unstandardized. And that, everybody, there it is. Found it. There's unstandardized. Just click right there. Standardized. There you go. It's right there. Oh, it's nice and point and clicky. That is one thing nice about Amos. It really does have a very nice, it does have a very nice interface. And there's the standardized estimates for each of those. So remember, look, 0.11 for relationship item 1, social support 0.33. Some of these are kind of low relative to others. Relative to others. So that, everybody, I believe, takes us through that. I mean, structure equation modeling is something I used to teach almost a semester course in this. So there's a lot of other things to think about, but I think it'll be good enough to get you going, at least with Amos and your model. Now, let me go over a couple of things here, everybody. What if you were really curious and you have two separate models and you want to see which one fits best? Obviously, you'll compare the actual estimates. But I do want you to know briefly about the information theoretic indices. There's the K-key information criterion and the Bayesian. Basically, what these are, they're a function of the log likelihood or the chi-square in the model and the number of parameters to be estimated. So a lot of times you can use the AIC or BCC to compare to other models. The lower, the better. The lower, the better. So here it's 153.87. Let's say you ran a new model, adding a path, deleting a path, and it goes down to 149. That means it's a better model. So these are really helpful when I look at alternative models. You're going to find these type indices are really helpful when briefly I'm going to discuss mixture modeling today. So these are, if you want to, you're not required, but for your take home, if you want to compare your two hypothesized structure equation models, these can be used for nested or unnested models. Nested or unnested. So that's just one more fit in this. Now what the heck do I mean by nested versus unnested? Well, the best way is for me to draw this. Does everyone see this basic four-construct model? Pretty clear, two exogenuses. This double curved arrow means the covariance between them, the mediator, and the endogenous variable. Both of these are endogenous's. So you go ahead and have this basic, simple model. Let's just pretend. I'm going to call this Model 1. I'm going to call this Model 1, and I'm going to say the chi-square equals 30. I'm just going to make up a number. And the degrees of freedom equals 5. And the AIC equals 32. I'm just making those up. Now, Jocelyn decides to add this path. She decides to add this path. I'm going to call that Model 2. The chi-square equals 24. Degrees of freedom is now 4. Do you see I've lost a degree of freedom? Why have I lost a degree of freedom? Why have I lost a degree of freedom?
Because you're specifying?
I'm adding a new path. And the AIC equals 30. So this model is nested within this one. Right? Or basically, or the way to think, I'm sorry, this model is, M1 is nested within Model 2. Because Model 1, which has more degrees of freedom, is a more restricted model. Because the way to think about it, Jocelyn is letting it estimate, right? Whereas Zach is setting it to what? 0. See, for Model 1, we're setting it to 0, right? You don't think that there's a path
Right.
from organization commitment to job satisfaction. Jocelyn is freeing this up to be estimated, which means you have one extra path to be estimated, losing a degree of freedom, which means that this model, the first model, is nested within the second model. The more restricted model is nested within the less restricted model. Chad, you keep looking back. Do you have
Yeah, I'd love
questions?
to have this, be able to refer back to this, but we're having some trouble getting, I'd love to be able to watch this later.
Okay. Do you have questions on this?
No,
or-
no, I'm good with the
Okay,
pattern.
okay, let me know, because I know this is a new vocabulary, but I really want to make sure you're understanding what I'm saying right now. Do you understand the notion of a nested model? One model is more complex than another. One model, Jocelyn says, Dale, I think it's really important to model organization commitment to job sat. Zach says, no, I've done some research, I'm not seeing a relation. So Zach is setting this path to what, everybody?
0.
Yes, whereas Jocelyn is doing what, Chad?
She's defining
Yes, she's estimating it, which means is her model more or less restricted?
more restricted,
Less.
less restricted.
It's less restricted because she's kind of having to estimate a little bit more. He is saying, no, you know what, no relation, fix it to 0. His model is actually, believe it or not, less complex. Hence, Zach has more degrees of freedom. He has a little more wiggle room. Because Jocelyn is saying, I'm going to estimate one more path. I'm going to make my model a little less parsimonious, a little more complex. So what's really cool about nested models, everybody, I can take the difference in the chi-squares. 30 minus 24 is 6. The degrees of freedom is 1. I can go to a chi-square table and do what's called a chi-square difference test. It's just the difference in the chi-squares, given the difference in degrees of freedom. And if it's significant, and I already know the critical value is 3.84 for 1 degree of freedom, is 6 bigger than 3.84? So guess what? Who wins, everybody? I'm looking that Jocelyn has a lower AIC, and let's pretend her CFI is better, etc., than his. She wins. So what's really cool, everybody, is you can start comparing alternative models for either nested models or unnested. What do I mean by non-nested? Zach adds a third variable. Zach adds job engagement to his model. That's not nested. It's just a different model. And here you can compare AIC for unnested models. You can't take a difference test. They got to have the same parameters, same constructs. So it's very, very rare, everybody, when I'm on a project and I'm not testing alternative models, some that are nested. And I do a chi-square difference test. A chi-square difference. So do you start to see some of the really cool flexibility that you have with structured equation modeling? To really, regression is great, but it sure kind of goes beyond regression in terms of testing these models. Now, any questions about interpreting the basic SEM? You guys aren't going to be experts by next week. This is something that I've spent years. I've been doing this for 21 years now. I'm still constantly learning about SEM. So you guys got enough with Amos to get going and not to cause undue harm. But that being said, if you really plan to do this for your dissertation, you guys, buy some of the books. Klein's book is a great book. I think Klein's book on principles of structured equation modeling is a nice, user-friendly, non-software book. If you want something that's more software, Barbara Byrne has got a book for Amos, for M+, for Lizerl. Tons of books out there, everybody. I do have, unfortunately it's a little old now, but I was asked by Journal of Child Clinical Psychology Center, I was asked a few years ago to write a review of all the intro books that are available. My review is on my website. It's now about 8 years old, so I think it's old. But I do have a review that's on my website that I reviewed all the intro books that were available up to that time. So let me discuss some other issues before I get you on a break.
Can I ask a question?
Sure.
What if you have a model and you versus the direction, and you have good fit for both of those models. Because I
Oh, then you know what I'm sure you've already read? What part have you read in the book, Zach?
I must have missed that part.
Really, Zach?
Yeah.
Really? Did you happen to read, Zach? Let's see if this helps you just a little. I'm going to bring up a term that you're going to say, oh, Dale, I did read that part.
Oh, Dr. Glaser.
Hold on. Hold on. Okay, it is in here. I just have to find it. Did you remember reading the part on equivalent models, Zach?
It's a little fuzzy.
A little fuzzy.
There's so much going on,
There is. Yes. Zach, you brought up what's called equivalent models. The fact is, 1, 2, 3. Chad might have this. You might have this. You and Chad, and guess what? Your chi-square for both, 20, 20. CFI, 0.93, 0.93. In other words, you may get equivalent fit for alternative models, and absolutely that can happen. They're both good models. It means that sometimes, you know what, there's alternative specifications for the same constructs. It is not unusual that there may be alternative ways of specifying your model that leads to ultimately the same solution. That's called equivalent model equivalency.
So if I tested 1, 2, 3, and 2, 1, 3, would I be testing alternative models, or are those not alternative models?
They're alternative models.
They're still alternative.
They're alternative for what's called competing models.
Okay.
They're not nested.
Just because they give you similar.
Similar chi-squares,
Yeah.
similar maybe parameter estimates are not that different. Absolutely. That we know that there can be a very similar fit with alternative models. Zach may have model number 1, Chad may have model number 2, and you know what? They're both not wrong. Now, be careful. You can't do a chi-square difference. Do you know why?
Because they're not nested.
They're not nested, and also they have the same degrees of freedom. Right? Remember, with degrees of freedom, nested means there's going to be less degrees of freedom for one of the models. So absolutely, you can have equivalent models that lead to the same fit, and then that's your decision. Theoretically, what makes most sense. And you'll be kind of doing, that may happen with your take-home. That may happen with your take-home. Though generally, historically, the data set I presented, they have led to different fit. Now, so that, everybody, again, is kind of a little bit of the lecture on that one. One thing I do want to show you. In your psychometric class, have you guys, how deep have you gone into CFA? This type of depth, or have you gone into measurement and variance? Because I don't want to be redundant with your class.
We're real surface level.
What's that?
We're real surface level.
What's your understanding of measurement and variance now?
That would imply some understanding.
That's one of the most BSy responses I've heard in a long time. That was very, that was good. That was good.
Invalidity.
That was good.
That is invalidity.
Measurement and variance is kind of what you got to do nowadays with CFA when you have a new instrument. I mean, it's almost like, I'm not saying everyone does it, but it is kind of where if you pick up an issue of psychological assessment, what they will do is, I have a brand new instrument. And I'm going to go ahead and organization commitment, professional commitment, and what's that variable I know, Bernard, is it engagement? What do you guys look at a lot? Employee engagement? I'm going to make this really messy. Job involvement. This is a really messy one. Why? Because they sure kind of seem the same, don't they? Some of them, right? So let's say I have organization commitment, professional commitment, employee engagement, and job involvement. Is it really clear, you guys would know much more about this than I. Is it clear that employee engagement is separate from job involvement, or is there kind of a lot of shared variance?
Job involvement is probably kind of included in engagement.
Well, I'm sorry, what's that?
It's kind of included in engagement. Sort of, there's a few different constructs that.
I bet there's a lot of. So here, let's say this is your dissertation. 4 constructs, and you want to do a psychometric testing, and basically it is a form of construct validity. That being said, measurement and variance goes through a sequence of steps. Steenkamp has one of the older articles in a marketing research journal. Then there's dozens of articles. Organization Research Methods has a great article by Lance and Vandenberg about the steps to go through measurement and variance. There's actually multiple steps. One is called configural invariance. I'm going to not worry about that for now, but I'm going to start with metric invariance. What does metric mean? Metric invariance means that the loadings, right? If I have something like this, that the loadings, and this is where you start to, where you get into this measurement and variance, everybody. Males and females. So now, guess what we're adding, everybody? Groups. Multi-sample CFA. So a big thing in psychometrics is, how do I know Chad's instrument here has the same fit for males? And Jocelyn says, Chad, do you know if this 4-construct tool has the same for females? And Chad, of course, says, absolutely. And then Jocelyn says, have you tested it? I don't need to. I know it's the same. So Chad says that with much bluster, and because he's professing that it's invariant across groups. But are they? Are we sure that all our westernized instruments translate well across cultures? This has come home to me in an applied setting, everybody, multiple times. The first time was over 20 years ago in a meeting in Sharp Healthcare on an illness dependency scale. We added a depression inventory. I feel blue today. We were down at Sharp Chula Vista, and they say, I feel blue today will not make sense to some of my buddies down in Guadalajara. They're saying, what do you mean I feel blue today? The translation, what? I turn blue?
Yeah.
I had a student from Germany who said the item, I feel down in the dumps, is translated to trawling through the trash. So these items that we take for granted in the USA, do they translate well in Germany, Korea, Vietnam, across different norm groups? So what's really cool, everybody, is the book discusses this briefly, called measurement and variance. In other words, is this instrument invariant across groups? So the first step would be called metric invariance. Are the loadings the same across groups? So I first do a multi-sample CFA and have everything free to estimate, everything. That'll be my model. Then I start restricting them. I have this be equal to females. That's called metric invariance. And if my model fits better, guess what? Is Chad happy or sad? If my model fits better, when I constrain these to be equal across groups, is Chad happy or sad? Yes, because guess what that's buttressing? His argument that the factor loadings are similar across groups. Number 2, Ross says, I'm really interested in if maybe the means are different or similar across groups. So you can do what's called scalar invariance to set if the means are different across groups. Then you can do what's called scalar invariance and strict invariance. Strict something invariance. I'm forgetting the word, I'm having a brain blip. But you can see if the errors are similar across groups or different. So it's really cool, everybody, psychometrically, is the beauty of being able to test these multi-dimensional constructs across groups called multi-sample CFA. I've done this multiple times. I've done this for quite a few clients the last few years, and they love it. That's something they haven't even thought about. And I said, what the thing is, are you sure that these models test the same? And you can do this as I did in one journal article with UCSD professor in social psych, where we looked at gender and risk-taking. We did regression path models for males and females on risk-taking, and you can also see if the path coefficients are equal or not. So you set these models, you constrain them to be equal, you gain more degrees of freedom, you do a chi-square difference test, and see if your model fits better. So again, this shows the incredible flexibility of being able to have multiple groups in terms of, and that's called measurement invariance, or these structural models. And that's just one little bit. So why don't we take a little break, take 15, we'll come back at 10:45.